Okay, so we'll go ahead and get started. Just a warning, my neighbors are doing some construction, so you'll hear some drills and banging every now and then, but I think we'll manage here. Okay, maybe before I get started, I'll just check in and see how everyone is doing. You guys submitted your first lab yesterday, and I took a quick peek, and it looks like a lot of you guys figured out the knitting and all of those issues. And if you had issues, or if you're still having issues or things like that, I will have office hours after lecture today, so you can stick around and I can try to help you guys out. A handful of people came during yesterday's office hours at 10 a.m. and I was able to help them. So we're here. I'm here and Eric's here. We're here to help you guys out. So don't hesitate to come to office hours. Okay, well, let's go ahead and take a look at today's lecture. Today we're going to take a look at sampling distributions, which as you can see, it says foundations for inference. And so this really forms the basis for a lot of kind of ideas regarding statistical inference, which is, the idea of making conclusions about the population based on the sample. So again, just to review a few key terms, because it's going to be important that we distinguish between the population and the sample. The idea is that you have some kind of research question, and that research question has a relevant related population, and the population would be everyone, all the people who are relevant to answering the question of interest. And the problem is that the population is always too big for us to study directly. Okay, the subject of statistics exists because we want to learn about the population, but we can't study the population directly because it's just too big. And so the key idea here is we select a sample. We don't look at everyone. We just looked at a selection of people, and that selection is known as the sample. And what we want is we want our sample to be representative of the population. It's really hard to guarantee that the sample is representative. We generally can't guarantee that a sample is going to be representative. So instead, we often rely on random sampling, or at least the idea of random sampling. And we hope that a random sample will be somewhat representative of the population. We can't guarantee that, but that's what we want. And so after we record information from this sample that we've selected, that is our observed data. And the whole idea of inference is that based on the data in our sample, we try to make conclusions about the population. Okay. And when we summarize a population, or when we summarize a sample, to distinguish the numeric summary for the population and sample, we use different terms. Okay, so a parameter is a numeric summary for the population. So if we're talking about the entire group, and we want to know what is the mean of the entire group, that mean of the population is known as a parameter. Okay, and then on the other hand, when you've taken a selection from the population, when you have your sample and you say, okay, what's the mean of our sample? The mean of your sample is a statistic. Okay, and today we're going to be mostly talking about the mean, but the idea here applies for any other kind of numeric summary. So if you're talking about the standard deviation of the population, that's a parameter. When you talk about the standard deviation of a sample, that's a statistic. Or the variance of the population, or the variance of a sample. Variance of the population would be a parameter. Variance of a sample would be a statistic. So any kind of numeric summary that applies to the population is a parameter. And again, the central idea is what we are going to do is we're going to look at a sample's statistic, and based on that, we're going to draw conclusions about the corresponding population parameter. So just a couple examples here. So one is perhaps an election is coming up, okay? and you conduct some kind of political poll, and it says a sample, let's say you select a sample of say 800 likely voters, okay, 800 likely voters. And so the population that we're really interested in isn't the sample, it's the population of all the voters who are going to show up on election day. That's the group that we're interested in. And we're trying to kind of make predictions or conclusions about that population. And so, but anyway, you survey your 800 people, that's your sample. And maybe in your sample, you get this statistic, a sample proportion of, say, I'm just making up some numbers here, and people is that maybe your sample proportion says 44% of people in the sample support candidate John Q. Public, right? So you've got some kind of candidate, and you say, do you approve? Are you going to vote for John Q. Public? In your sample, 44% out of those 800 say, yeah, we will support John Q. Public. Okay, and so the question is, based on the statistic, based on what you see in the sample, what can we say about the parameter, the proportion of all the voters? Does that mean John Q. Public will get 44% in the population, or will John Q. Public get a different proportion in the population? That's what we want to know. Okay. Another example, let's say you're dealing with some experimental blood pressure medication, and you have 50 volunteers, right, to participate in the study. The population would be everyone, basically all potential patients, everyone with high blood pressure who might take the medication. And so, when you do your experiment, you randomly assign people to medication, randomly assign some people to take the placebo. And let's say at the end of the study, you observe kind of the following numbers. And we'll say the mean blood pressure of patients in our sample who took the medication, maybe their mean blood pressure, we'll say their systolic blood pressure is 125 millimeters of mercury. Whereas when you look at the mean blood pressure of patients who took placebo, maybe that mean is 135 millimeters of mercury. And so what we're observing is a difference of 10 millimeters of mercury, right? 10 points between this mean 135 and this mean 125. And what we want to do is we want to make conclusions about the parameter in the population, which would be kind of the difference between mean blood pressures of everyone who might take the medication versus placebo. So in the population, this hypothetical population, there exists some kind of mean difference, and that's what we want to make conclusions about. Again, to make sure that we don't get these terms and ideas mixed up, we use different symbols as well to distinguish statistics from parameters. So if you're talking about the mean of a sample, the symbol you use is Y bar, whereas the mean of a population, the symbol is mu. The standard deviation of a sample is S. The standard deviation of a population is sigma. Okay. So basically, you see the Greek letters, it's going to be a parameter. The sample proportion for the sample, we put a little cap over it. It's called p hat. Okay. And then when you have the population proportion, it's just p. Okay. Population proportion is p, nothing over it. Proportion in your sample proportion is p with a little cap. It's called p hat. P hat. Okay, and this is old news, but sampling is the process that we go through in order to select individuals from the population to be in our sample. And what we want is a sample that's representative. If it's not, we could say it's biased. And the method that should produce representative samples is simple random sampling. but again, it's not guaranteed. Okay. We have a question that says the only difference between these two variables is that parameters are for populations. Yes. So well, I wouldn't say the only difference, but the key idea here is that parameters correspond to populations, samples, statistics correspond to samples. And there's kind of a match, right? You have the mean of the sample, you have the mean of the population, okay? And so they're kind of, it's the same idea, except one applies to the population, we call that a parameter. One applies to the sample, we call that a statistic. Maybe some examples might do us a little bit better. Okay, so this next part, I'm going to introduce this very important idea of a sampling distribution. A sampling distribution. Okay, so when we do random sampling, a key idea here is that the individuals that end up in your sample are random, and therefore, when you calculate a statistic from one sample and the same calculates the same corresponding statistic for another sample, you're going to get different values, even if they come from the same population, right? So you could take from the population, maybe you have I don't know, you're looking at rabbits or something, right? And you select 10 random rabbits, okay, and you weigh them. And you get the average weight of these 10 rabbits. I have no idea how much a rabbit weighs, right? Let's say is 500 grams, okay? So the average weight of these these 10 random rabbits, let's say, is 500 grams. Okay, somebody else goes and finds another set of 10 random rabbits, and they take the average weight. Is their average also going to be exactly 500 grams? Probably not. It might be something like 508 grams, maybe 470 grams. Okay, who knows, right? And then the idea is that the statistic, when you take a random sample and you calculate the mean of your sample, that number is going to vary from one random sample to another random sample. Okay, so it says for a numeric variable, the sample statistic is the sample mean. And when we take a random sample, we expect the sample mean to be close to, but not exactly equal to the population mean. So perhaps we actually know what the population is, okay? And like the mean of the population. So we know that the average weight of a rabbit is some number, and some rabbits are bigger than that, some rabbits are smaller than that, but perhaps we know what the mean of the population is, okay? And so when you, so here, the example here is, let's say we have a population. The population has a normal distribution, and the mean of the population is 16, and the standard deviation of the population is 5, okay? And so when you draw a random sample, let's say we're going to just draw 5 random observations from this population, and you take the mean of your sample, we expect the mean of that sample to be close to 16, but not necessarily exactly equal to 16, right? So, so let's just think about this for a bit, right? So I can kind of simulate drawing random samples here. Let me so in R, you can say I want 5 random values where the mean is 16 and the standard deviation is 5. Okay, and you know what? I'm going to just round these off to say 2 decimal places. Okay, and so here, if I draw 5 values where the mean is 16 and the standard deviation is 5, these 5 values I get 16.94, 14.85, 17.0, 18.36, 13.5. Okay. Here's another random sample. Let's the 5 values this time are this, and the mean of these 5 values is 15.674. Okay, let me just try this again. 5 values that time is 13.42, 21.2, 20.2, 9.99, 13.71. And when you take the mean of these 5 values, we get 15.692. Okay. Here's another example. I'm just drawing 5 random values from where the theoretic mean is 16, and then we're just calculating the mean, and I'm getting means that are a little bit different from 16, 14.476, okay? And I can just do this over and over and over again. Yes. Okay, so here's another random sample. I can ask for the mean here. Do this. Okay, so here's 5 random values, and the mean is 18.106. Here's another 5 random values, and the mean is 14.9. And the population, the mean is 16. Here's 5 random values, and the mean is 16 there. Okay, and so this is what we want to do. We want to just kind of try this out, and we want to see what kind of values do we get for the mean of a sample of 5 random values. Okay, right, and so the question is, if we take a sample of 5 random values drawn from the population, could we get a sample mean that's close to 15, right? And we look at it and we say, oh yeah, here's a sample mean that's close to 15. That happens, right? Here's a mean that's 14.47. Here's another mean, I don't know, 15.6. So when you draw 5 values from this population, where the mean of the population, we know that the mean of the population is 16. It comes from a normal distribution, which means 95% of them are 95% of values are within 2 standard deviations of the mean, meaning they're between 6 and 26, 95% of the time. Can we get a sample mean where the mean is 15? Sure, that's going to happen quite a bit. Okay. Can you get a random sample of 5 values where the mean of those 5 values is only 13? Is that going to happen? Okay. And yeah, that could happen. Maybe not as frequently, but it could happen. Okay. So here's let's see if we have 13.996. Okay, so here's one where it came down 12.3. So, a little bit farther away from 13. So it happens, but not as often. Could we get a sample mean close to 10? Again, we're drawing 5 random values. Could the mean of those 5 random values end up being as low as 10? And the answer is, yeah, it could happen, but it's pretty unlikely to happen. What about a sample mean of 8? You draw 5 random values, okay? And again, we're drawing 5 random values from a population where the mean of the population is 16, okay? So if the mean of the population is 16 and with a standard deviation of 5, could you get 5 values where the mean is as low as 8, right? And the answer is, it's possible, but it's really, really unlikely, okay? What about 5 values where the mean of those 5 values is 3? Could that happen? Okay. And the answer is, it's not impossible. The probability is not 0, but it's pretty close to 0, right? Because 95% of our values are going to be between 6 and 26. And so for the mean to be 3, then that means kind of like all 5 values have to be like below 6. All 5 values have to be something like 3, maybe 2, 3, 4, something like that. And those are pretty unlikely individually. That's a pretty unlikely value to get in the first place. And then to say a random sample of 5 values is going to end up where all 5 individuals have values this extreme. That sounds like that's really, really, really unlikely to happen. Okay. So we write, theoretically, it is possible, but it's incredibly unlikely. Okay. And so while all of these outcomes are theoretically possible, just intuitively, we know that most of the time our means are going to be kind of closer to 16, like somewhere between 14 and 18 or something. And means that are way out here should be, should very, very rarely happen. Okay. And so this gets us to the idea of the sampling distribution. The sampling distribution is the distribution of the possible sample statistics. Okay. It's the idea of what is the probability that a random sample of a certain size produces a particular value for that sample statistic. Okay. So if we're talking about the mean of a sample, say y bar, we can talk about the sampling distribution of y bar, the sampling distribution of the mean. Okay. And it tells us which sample means are more likely, which sample means are less likely. Okay. What we can do is we can kind of simulate the creation of a sampling distribution. And I'm going to open this little web app here. And the diagram here is this giant kind of potato looking thing is supposed to represent our population. It's supposed to be the big entity that we cannot observe directly. And so instead of trying to observe the entire population directly, what we will do is we draw a random sample of a given size, size n. In the beginning, we'll start off with 5 or something. And we're going to calculate the mean of this random sample, and we write down y bar 1. Okay. Then we go to the population. We do this again. We draw a different random sample of n values. We calculate the mean of that second random sample, and we get y bar 2. Okay. We do this again a third time, another random sample of size n, and we calculate y bar. We do this another time, another random sample of size n, and we calculate y bar. And we do this over and over and over and over and over again. Every single time, we're going to get a slightly different y bar. Okay. And we're going to keep track of all of the different y bars that we have. And then we'll produce a histogram of all the different y bars that we get. Okay. And that will give us a sense of the sampling distribution. It's a simulated sampling distribution, but it's the idea of which values of y bar are common and which values of y bar are unlikely to appear. Does that concept make sense? As far as the creation of a sampling distribution, we just want to see what kind of y bars can we get. Okay, thank you for that thumbs up. All right, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter C. C as in cat. C as in cat is the first view quiz answer today. Oh, okay, so let me click this link, and here is the app. Okay, and so this thing up here, it's labeled parent population, okay? And the parent population has a normal distribution, right? And so I'm gonna click this button animated, and it's gonna say, we're gonna select a sample of size 5. We're gonna calculate the mean of that sample of size 5, and it's going to calculate the mean of those 5 values, and then it's gonna just kind of drop a little brick down. Okay, so here's 1, 2, 3, 4, 5. 5 random values drawn from this population, and it puts a little brick down here. Okay, and because this is normal, you're going to see most of the values coming from kind of the middle area, right? You're going to see more values coming from the middle. Occasionally, you'll see values out here and values down here, and very, very rarely, okay, it'll be very rare for us to see a value out here or a value down here. Okay. That's what it means to be normal. Most of our values are going to be coming from around here. Of course, we're going to get an occasional value from up here, occasional value from down here, but very rarely will we see values extremely low or extremely high. Okay. So here's another 5 values. These all 5 values kind of came from the middle. What's the mean of these 5 values? We drop a brick in the blue area right here. Okay. We do this again. Here's another 5 values, right? So we have one that's a little bit lower. Most of the values come from up here. The mean of those 5 values goes right there. Another 5 values. Okay, what's the mean? And every single time we draw 5 random values and we calculate the mean, of those 5 randomly selected values. Okay, and so we can sit and do this all day. We're not going to, but hopefully this little animation gives us a sense of kind of how we are building up the sampling distribution, right? And so we can see just the individual values. And so sometimes, you know, your sample of 5 values, you get values down here and values up here. But again, we're calculating the mean of the 5 values, and the mean of those 5 values ends up wherever the blue block drops down, right? So the mean of these 5 values is down here. Okay. And so the question is are we ever going to see a mean where the mean of the 5 values is up here? Or are we ever going to see a mean, a sample where the mean of the 5 values in our sample ends up down here? Okay. And I think we can kind of see that, you know, it's not impossible, but it seems like that's almost never going to happen, right? For us to get a sample of 5 values where the mean of those 5 values is going to end up down here, or the mean of the 5 values is going to end up over here, right? So you might get one individual extremely high, and we saw an example just there where we got one individual like way out here. You might get it one individual, but for the sample, for all 5 in your sample to end up with a mean really extreme seems pretty unlikely to happen. Okay, so I've done this a bunch of times, and there's a little like shortcut buttons where you can kind of do 5. When you click this 5, it's doing 5 random samples, and it doesn't bother showing the individual values, but just plots kind of 5 additional bricks down here. And then what do you think is going to happen? So I can just go ahead and get to the end and just click 100,000 here. What kind of shape are we going to see down here if I click 100,000? So that's going to do 100,000 samples of 5. What do you guys think we will get? Okay, so some of you guys are writing normal distribution. And indeed, that is what we get. We get a normal looking distribution. You can plot a fit normal, and we can see the normal curve fits almost perfectly over the distribution here. Okay, what if I take a different sample size? So instead of n equal to 5, what if I did n equal to, say, 20? What do you think it will look like? How do you think it will compare? So here's n equal to 5. This is kind of what it looks like. What if I do n equal to 20? What is the resulting distribution going to look like? Okay, well here, let me just show you what's going to happen, right? So here is, it takes a while to do the animation because it's drawing 20 random values from the population. And it says, okay, here's 20 people. And what's the mean of these 20 values right here? Okay, here's another 20 values. And so, you know, when you take a sample size of 20, sure, you might get an individual way out here. You might get an individual way out here. But when you take the mean of all 20 people, even though you have one really high value or a really low value, the mean ends up being kind of close to the middle, right? All right, so here's another 20. Okay, what do you think the resulting shape is going to look like? And what do you think the resulting width is going to look like? How do you think the width of this distribution will compare to the width of the previous one, right? Okay, so the width is going to be, yeah, not as wide, more towards the middle, more condensed. Yeah, so if I go ahead and click 5 at a time, and then I'll just go ahead and shortcut to the end 100,000, this is the resulting distribution. Okay, so again, here's n equal to 20, n equal to 5 looks like this. The standard deviation for n equal to 5 is 2.23. That's a normal distribution. If I do n equal to 20, we also get a normal distribution, but it's a lot more narrow. The standard deviation is only 1.12. Okay, and we can see kind of, you know, I can do 2 at a time or whatever. And so when you do 2 at a time, the resulting distribution is quite wide, okay? Because what happens here is yeah, most of the time we're going to get values, but is it, getting one value way out here is not going to be common, but, and getting two values way out here is not going to be a common thing, but it's possible, right? When you're only selecting samples of size 2, it's possible to get a random sample. Let's see if we can get a random sample where the mean ends up down here or the mean ends up down here. All right, so when you're only selecting 2 people, when you're only selecting 2 random people, it's possible for your random sample of 2 to end up fairly extreme, right? By random chance, you can get 2 people who are really tall, or by random chance, you can get 2 people who are really short, okay? But if you select 20 people randomly, when you select 20 people randomly, what's the probability that all 20 end up being extremely tall or all 20 end up being extremely short? Okay, that becomes a much lower probability. So when you have samples of size 2, you have a wide spread. When you have samples of, say, 20, you have much less spread. And basically everything in between is something in between. As you increase your sample size, the spread decreases and decreases and decreases, okay? And that's what we have here, okay? And I wrote a little script here to illustrate this as well. Let me see if I can run it. Okay. Oh, you know what? This was actually something different. Okay, sorry. I got ahead of myself here. Okay, so this is, we had a normal population and this is what it looks like, okay? So the question is, okay, what would happen if we didn't have a normal population, but we had a different distribution, okay? So what if instead of a normal population, we had a uniform population? A uniform population, okay? Well, what would happen when I take samples of size 2? Okay, samples of size 2, okay? So with a uniform, we're saying all values, the lowest and the most highest and everything in between all have an equal probability of being selected, okay? So this has an equal chance of being selected as this value. Every single value on the number line has an equal chance of being selected. That's what this uniform distribution means. All values have an equal probability of being selected. Okay, what do you think the resulting distribution will look like when you take samples of size 2? So here I'm taking samples of size 2. And so as I do just a few at a time, this is kind of what the distribution starts to look like. And I think this might be a little bit of a surprise, but the resulting distribution ends up looking like a triangle, okay? When you only take 2, you end up getting a triangle, okay? And so let me kind of illustrate with dice, okay? If I said, how many ways are there to get for 2 dice to add up to 2? There's only one way, right? Okay, what about for dice to add up to 3? Okay, you can have 2, 1, and you can also have 1, 2, right? There's 2 ways for the dice to add up to 3. Okay, 2, 1, and 1, 2. Okay, so you have 2 ways, right? What about dice adding up to 4? Okay, dice adding up to 4, there are now, you have 3, 1, you have 2, 2, and you have 1, 3. Okay, there's 3 ways. Okay, and if you think about how many ways are there to make 5, there's going to be 4 ways. There's 1, 4, 2, 3, 3, 2, 4, 1. Okay, and it forms kind of every next number, there's one more way to get it. Okay, and so that's what we see until we get to the middle. And then, so there's going to be 6 ways to form a 7. Okay, and then how many ways are there to form an 8? Well, there's only 5 ways. How many ways are there to form a 9? There's only 4 ways. How many ways are there to form a 10? There's only 3 ways, and so on and so forth until you get to 12, where there's only 1 way. And so you have kind of a linear trend of increasing methods to form these things, and then an decreasing trend until you get to the end there. All right. So that's what we see there. So with n equal to 2, we get this pyramid. But then when we get to n equal to 5, we get something that looks like the normal distribution. With n equal to 10, it ends up, it's definitely looking like a normal distribution. So there's something that happens between n equal to 2, where we get a pyramid, and n equal to 10 or something where we get something that looks like the normal distribution. And so to kind of do this, I wrote a little script. This represents the population, values 0 through 32. All have an equal chance of being selected. Okay, and what I'm going to do is I'm going to basically draw a random sample from the population. So store that into my sample, and then I'm going to calculate the mean of that sample, and I'm going to keep track of this, and I'm going to create a histogram. All right, so I'll go ahead and so here I'm going to run for sample sizes from n equal to 2 to n equal to 25. Okay, so that's all done. So if we start off at 2, we see we get that same kind of pyramid triangle distribution. For n equal to 2, we get a pyramid. Okay. At n equal to 3, we get a little bit of rounding out. And as we increase, so here's n equal to 5, 6, 7, what we can see is this starts to look more like a normal distribution. And we also see the other phenomenon happening, which is that the spread of the resulting distribution ends up getting more and more narrow, right? The center gets taller, and the spread gets, the resulting distribution becomes more and more narrow, right? The more extreme values become less probable, and we get something that's more concentrated around the middle. Okay, and as you know, if we go in the opposite direction, as n decreases, the distribution gets wider and wider. Okay, so the question says, aren't uniform distributions supposed to be rectangular spaced as we increase the sample size? So the original uniform distribution is in the shape of a rectangle. Okay, but again, what we're doing is we're drawing random samples of, say, 2 or 3 or 4, and we're plotting the mean of that random sample. And when you plot the histogram of the mean of the random sample, it ends up taking on these different shapes, where eventually it looks like the normal distribution. I'd say around n equal to 8 or 8, 9, 10, it looks like the normal distribution. And here we get, at n equal to 2, it's not normal. It looks like a triangle. But yeah, this is not quite the same here. Okay. Let's see, we have a question that says, how do you get different mean values if all the values are the same in the uniform distribution? Okay, it's random. It's random, right? So again, rolling dice is like a uniform distribution, right? All the numbers 1 through 6 have an equal probability of appearing. Okay. So the question is, how are we ending up with different mean values? Okay. Well, if I throw 2 dice and I say, what's the total of those 2 dice? The mean and the sum are pretty much the same thing. It's just the mean is the sum divided by some constant, right? So if we say, what's the total of its 2 dice, the mean of the 2 dice would just be the total divided by 2. Okay, so if I roll the 2 dice, even though all numbers show up with equal probability, you can get the sum to be as low as 2. You can get the sum to be as high as 12. You can get the sum to be 7 and things like that, right? And 7 is going to appear more often because when you roll 2 dice, there's 36 possible combinations. The 7, there's 6 ways to make a 7. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Okay, there's 6 ways to make a 7. Okay, 7's going to show up a lot more frequently, whereas say the number 2 will show up a lot less frequently. There's only one combination out of the 36 that results in a 2. right? So when you roll the dice, when you roll 2 dice, which is kind of what we're doing here, except you can think of it as like a 32-sided die, okay? When you roll the dice, the sum or the mean can end up being different because it's random, right? Sometimes you get, sometimes you get a 6 and a 5 and you get a sum of 11. Sometimes you get a 1 and a 2 and you get a sum of 3. And sometimes you get a 3 and 4 and you get a 7, or a 5 and a 2 and you get a 7, and things like that, right? And that, I mean, that forms the basis of some Las Vegas casino games, like craps. That's a, if you like gambling, that's a fun game. It's a popular game because it's almost like a team activity. But yeah, you roll the die, and if you roll a 7 on your very first roll, you actually you win money. And then if you, yeah, it's okay. There's a bunch of rules, but there's all of these other combinations where you lose money and things like that. Okay. So that's the sampling distribution there. And I drew a plot of this, right? N equal to 2, and different sample sizes with, sample size of say 20 or something, it ends up looking like the normal distribution. Okay. Here's something interesting that also happens. Okay. What if our population was not normal, but was, you can actually change the shape of the population, something like this. Okay. All right. So what if I have this? Okay. And so here's the population. It's going to either produce a value between 0 and 5 or 27 and 32. Okay. And it will never produce a value, from say 6 to 26 or something like that. Okay. So the mean is 16, but the values themselves that get produced, they're either going to come from up here or come from down here. Okay. So here are, you can get values from here, values from up there. The average of these two values is right there. Okay. 2 values right there. Sometimes you get both values from up here. Sometimes both values come from down there. Okay. What do you think the resulting distribution will look like? Okay. Do you think it'll look? Okay, so some people have written, they think it might look like the normal. Someone wrote they'll get 3 pillars. All right, so this is what we end up getting. We get 3 triangles, 3 triangles. Okay, so we basically get a triangle for down here, and this is kind of like if both numbers come from the low end, yeah, you get kind of this triangle distribution because it's basically uniform over here. And when you take 2 values from the uniform, maybe you get a triangle that looks like this. And you also have a triangle up here. And this is like what happens if you get both values from up here. You get 2 triangles. And then you have basically a triangle in the middle that's twice as tall. And that's because that could happen if you get 1 value from the low end and the second value from the high end. It could also result in that when you get the first value from the high end and the second value from the low end. And it's twice as tall because there's kind of 2 ways to form something that ends up in the middle there. Okay. Does that kind of make sense? So we end up getting 3 triangles here. And so we can actually do this as well. Let me clear out all of these plots here. So we can get values from 0 through 5 or 27 through 32. And then I'm going to go ahead. And so here it is for n equal to 2. And I'll just kind of let this run, but we'll cycle through. This is the computer kind of simulating a bunch of these different results. Okay, so let's take a look here. So back when n equals to 2, we see we get 3 triangles here. At n equal to 3, we get 4 triangles, okay? Basically, if all 3 values come from the low end, all 3 values come from the high end, 2 from the low, 1 from the high, or 1 from the low and 2 from the high, okay? So we end up getting 3 triangles, 3 spikes, and as n equal to 4, now we get 5 with n equal to 5, we get 6 of these things. With n equal to 6, we get 7 of these spikes, and so on and so forth. And we kind of keep increasing these. And at a certain point, the different spikes, they all kind of start to overlap and merge into each other. So as n equal to 10 or, around 16, they start to kind of blend together. And, we have a little bit, it's not quite normal, a little bit of artifacting and whatnot. But by the time we get to something around 23, 24, 25, this looks a lot like the normal distribution, okay? So even though our population, when we started, was anything but normal, it was something very, very dichotomous, right? You can get values way down here, values way up here, and nothing in the middle, okay? When I have a large sample, n equal to 25, the result ends up looking a lot like the normal distribution. Okay, we have a question that says, what sampling distribution would you need for it to be skewed to the right or skewed to the left? Is it possible for it to be skewed? Yes, I don't have any skewed examples in my notes, but you can draw a skewed distribution here. And yeah, and when you take small sample sizes, the resulting sampling distribution will start off skewed. Okay, and as you increase the sample size, okay, it's still a little bit skewed, okay, but as you increase the sample size, it becomes more symmetric, right? There's still a tiny bit of skew. It's not quite perfectly symmetric, but as you increase your sample size, the resulting distribution becomes more symmetric and looks more like the normal distribution. Okay, so here it is with n equal to 25. But of course, yeah, when you take small sample sizes, the resulting sampling distribution does not look normal. Okay, so all of this, here, and again, here's the pictures saying it looks a lot like the normal distribution. All of these pictures and things are just to kind of show us that when we run these things, the shape of the sampling distribution becomes normal, but it's under a condition, as long as the sample size is big enough. So when we had small sample sizes, like samples of size 2 or 3 or 4, it didn't quite look normal. But when we got to sample sizes of, say, 25, that's when the resulting sampling distribution looked normal, okay? Now, one thing that you might notice, if you, the link is in the notes, so you can kind of click and play. But when we look at the mean of the population, okay, if the mean is 16 and we take samples, okay, no matter what size the sample is, the mean of our sampling distribution is going to be 16 as well. Maybe a tiny bit higher, tiny bit lower, just because this is still a little bit of a random thing. But we get something, very, very close to 16, 15.99, maybe 16.01 or something like that. Okay, whatever the mean of the population is. Okay, so the mean of the sampling distribution is equal to the population mean. And then one thing we also noticed was that as we increased our sample size, the spread of our sampling distribution got smaller and smaller as well. So the standard deviation of the sampling distribution, and we give it a special name, it's called the standard error. The standard error, or the standard deviation of the sampling distribution, will shrink as the sample size increases. And so the standard error is given by this formula, sigma of, I don't know what happened here, y bar, should say sigma of y bar, not bar y here, is the standard deviation of the population sigma divided by the square root of n. So as n increases, it's in the denominator, it's under a square root, but as n increases, the standard error, or the standard deviation of the sampling distribution, shrinks because n's in the denominator. And so what we saw, where things start to look like the normal distribution, that phenomenon is kind of summarized in this thing called the central limit theorem, okay? the central limit theorem states that no matter what the distribution of your original variable, no matter what that distribution looks like, if your sample size is big enough, then the sampling distribution of the mean, sampling distribution of y bar, can be approximated by a normal distribution. So no matter what the population looks like, if the population, is skewed or is dichotomous or uniform or what, no matter what it is, eventually, if you take a big enough sample, it's going to look like the normal distribution. So the question is how big does your sample have to be, right? How big is large enough for us to apply the central limit theorem where we say, yeah, it's going to look like a normal distribution, right? All right, and so here's kind of our governing rule. If the population is normal, if you know the population has a normal distribution shape, unimodal, symmetric, then any sample size is going to be large enough, right? So when we started off, I think our first example was the population was normal. We had sample sizes of 2. That resulting sampling distribution still looks normal, okay? But if the population is not normal, then you'll need larger sample sizes, right? So when we switched over to a uniform population, sample sizes of 2 resulted in a triangle. Didn't look like the normal distribution. We needed a bigger sample size, like a sample size of 8 or 10. And then by then it looked like the normal distribution, okay? Rule of thumb is a size of 25 is considered large enough for most cases. So if you have a sample size of 25, it's probably going to be big enough for most situations. But if you have some really skewed data, right? If your population is skewed, then maybe even a sample size of 25 isn't going to be big enough. But in general, 25 is going to be big, right? And then there's kind of a flip side is that, if you're doing random samples, you rarely run into this problem, but you don't want to sample so much that you end up sampling, say, more than 10% of the population itself, okay? This rarely is an issue, but the idea here is if your sample size becomes so big, then what you observe in your sample ends up kind of affecting what remains in the population. So maybe an example that makes more sense is like if you think of a deck of cards, the very first card you draw at random has a 50% chance of being black or red, right? Because you've got 52 cards on the deck, 26 are red, 26 are black. The very first card you select has a 50% probability of being, let's say, being red, okay? After you draw that first red card, then what remains in the deck, now you have 51 cards and you have 25 red and 26 black cards, okay? And so therefore the probability of drawing a red card again is no longer 50%, but it's something a little bit lower, okay? And the idea is that, if you're only selecting, say, less than 5 cards from the deck, how much it's going to affect and change isn't going to be a huge deal, okay? But once you start selecting more than, say, 10% of the deck, once you start selecting more than 10 cards from the deck, then what remains in the deck could be significantly affected by by what you have in your hand. So, when we're drawing samples from the population, you don't want to select more than 10% of your population. Again, generally your populations are like millions of people big, millions of observations. So we rarely run into this problem. Okay, let's try this example out here. Okay, and I'll go ahead and I will work us through the solution here. Okay, it says the pulse rates of adult women in the United States are approximately normally distributed with a mean of 74 beats per minute and a standard deviation of 13 beats per minute. Okay, so we're going to say pulse comes from a normal where the mean is 74, standard deviation is 13. Okay, what we're going to do is we're going to select a sample where n is equal to 36. And the question is, what is the probability that the mean pulse rate, okay, so what is the probability that the mean, so we're going to write y bar, then the mean is under 71. Okay. What's the probability that the mean pulse rate of the sample is under 71? So what we have to do is we apply the central limit theorem. And we're going to say y bar comes from a normal distribution where the mean is mu and the standard error is equal to sigma over the square root of n. Okay, so y bar is going to come from a normal distribution where the mean is 36 and our standard error is going to be 13. I'm sorry, not 36. The mean is 74. Okay, the mean is 74 and the standard deviation or the standard error is 13 divided by the square root of 36. So we get 13 over 6, I get 2.167. An extra decimal, 2.1667. Okay, so this is what I have. All right, and then so at this point, now it's just a regular old normal model problem. The mean is 74. We're drawing a line at 71, and we're going to shade everything to the left of 71. So my z-score, 71 minus 74 divided by 2.1667. So what is that? Six. All right. And I'm going to have 3 divided by, negative 3. So negative 1.38. Negative 1.38. Okay. I go to my reference tables. With a negative 1.38. Negative 1.3. 0.0838. 0.0838. That's from the table. Okay. I hope I did that correctly. 0.0838. I messed something up. Okay. Okay, yeah. Clicked the wrong thing here. Okay. So y bar comes from a normal distribution with mu equal to 74, standard error equal to 13 over the square root of 36, 2.167. Z is going to equal to negative 1.38. We look that up in the table and we get 0.0838. And that's our answer there. Okay. Does that make sense? All right. Why don't I give you an exercise here and you guys try this out. Let me also give you your second view quiz answer. Today's second view quiz answer is the letter D. D as in dog. D as in dog is our second view quiz answer. Second view quiz answer is D. D as in dog. Okay, why don't you just do this first one? What's the probability that the sample average will be greater than 36? Okay, and we're talking about the partial pressure of oxygen, PaO2. And in the population, when we're looking at newborns, normal distribution, average of 38, standard deviation of 9. We are taking a random sample of 25, I guess, random newborn baby measurements from 25 random babies. Okay, and here, just do this first one. What's the probability that the sample average will be greater than 36? Okay, I'll go ahead and I'll pause the video, and then once you get your solution, go ahead and give me a thumbs up. And when a handful of you give me a thumbs up, we'll go over the answer. Okay, so let's go over our answer here. All right, so we have the PaO2. The measurements themselves come from a normal distribution where the mean is 38 and the standard deviation is 9, okay? We are taking sample sizes of 25, and so we're gonna apply the central limit there. And we're gonna say that the mean of a sample comes from the normal distribution where the mean is mu and the standard error is sigma over the square root of n. Okay, so we're gonna have the normal distribution where the mean is gonna be the same, 38, and the standard error is going to be 9 sigma divided by the square root of 25. So 9 divided by 5 gives me 1.8. All right. And we want to know what's the probability that the sample average will be greater than 36. So we're going to ask what's the probability that y bar is greater than 36. And what we have is y bar comes from a normal distribution centered at 38, mean of sigma 9 over the square root of 25. 9 divided by 5 is 1.8. Okay, so our picture looks kind of like this. The center is 38. We're drawing a line at 36. And we want to know what is this area over here. Okay, so we'll find a z-score. The z-score is 36 minus 38 divided by 1.8. I get 2 over 1.8. I think that's 2.22, but I'll just check. 2 divided by 1.8. I'm sorry, 1.11. Okay, 1.11. So z is negative 1.11. What's the probability that z is greater than negative 1.11? Well, using the symmetry shortcut, this is equal to the probability that z is less than positive 1.11. And we can go to our table. And I will look up the area to the left of positive 1.11, and I get 0.8665. Okay, did I make a mistake? Yes, thank you. That was a typo right there. Okay, 36 minus 38 is negative 2. Negative 2 divided by 1.8 gives me negative 1.11. And we want, what's the probability that z is greater than negative 1.11? I can look up negative 1.11 and find, just do 1 minus that, or I can say, well, the area to the right of negative 1.11 is the same as the area to the left of positive 1.11, and we get 0.8665. That's our answer right there. Okay, the other problem I'll let you guys do in your own time there. Okay, so I hope we're feeling okay about all of this. All right, let's talk about confidence intervals. Okay, so the goal is we want to do statistical inference, all right? And we want to make conclusions about the population based on a sample. And again, the general idea there is when we observe a random sample, we want to say, what can we say about the population based on what we see in the sample, right? So here's just this kind of silly example. We're going to say, we observe a sample of 16 randomly selected butterflies, randomly selected monarch butterflies. And I don't even know if it's physically possible to get a random sample of butterflies, because I feel like you're just going to be going out there with a net chasing down butterflies, and it's just going to be whatever butterflies happens to be there, and they're probably all like genetically related or something, but I don't know. Somehow we're going to get a random sample of butterflies. Maybe we've traveled around the world and we've caught a bunch of butterflies and we got a random sample. I don't know. I don't know how this is going to work. But let's say we do this, okay? And then we measure the wing area, the area of the wings. And again, this is like a delicate process, right? I think you have to like put them on graph paper and then you kind of like trace them and you see how many like squares they've covered and things like that. You know, people study bugs and butterflies and things like that. Okay. This is completely unrelated, but I remember seeing a documentary where they were like curious about these butterflies. And so they captured a butterfly and then they glued like a little GPS tracker on the back of the butterfly. And they were like, they had to like find the biggest butterfly they could find. Because even though these are like tiny little GPS trackers, it's like compared to a butterfly, it's like half of its weight. So, you know, some poor butterfly had to carry around this GPS tracker. But, you know, they were able to kind of study the migratory patterns of these butterflies and try to, I don't know, I guess protect their travel routes and habitats and things like that. But anyway, late nights on YouTube, I guess. Okay. What can we say? The question is, all right, this is our sample. You get a sample on of butterflies and you measure their wings. And the question is, okay, well, this is what we saw in our sample. Based on what we saw in our sample, what can we say about the population of all butterflies out there, right? Population of all, I should say monarch butterflies out there, okay? And so question is the mean of the population 30, right? In our sample, the sample mean was 30. Does that mean the population mean is 30? Okay. And, you know, I think our answer is no, the population mean is not necessarily equal to 30. But if I think about it, I would expect the mean of the population to be close to 30, right? If my sample has a mean of 30, I expect my population mean to be kind of close to that, right? And so, you know, maybe we can create a range or an interval of values that express what we think the mean mu could be. Okay, what could that population mean mu be? Okay. Our question says, can we not say for sure it's 30 because our sample size is less than 25? So it's not that the reason why we can't say it's for sure 30 isn't because our sample size is less than 25. I mean, that plays a role in the uncertainty, but it's just the fact that it's a random sample and that because it's a random sample, the population may not necessarily have the same mean as a random sample. Okay, so put these thoughts and ideas on hold, because this is what we want to do. We want to say, what's the mean of the entire population, this entire group that we can't view? Okay, what we've seen a sample. We know the mean of our sample is 30. What does that say about the population? Okay, all right, so put that thought on hold. I'm going to draw this picture. This represents the pinnacle of my artwork achievements here. This is a picture of a dog on a football field, okay? So this dog is standing on the 30-yard line of the football field, okay? And this is going to form an analogy of what we're doing with a confidence interval. Okay, so dog is pictured on a football field at the 30-yard line, okay? And here's the weird thing about this picture is that the dog's owner is also somewhere in the picture, except the problem is that the owner is invisible and they also have, the dog's actually going for a walk and the leash is elastic, but that's also invisible, right? So we have an invisible man taking his dog for a walk and he's got an invisible elastic leash, okay? And the question we're asking is, where is the owner located? Where is the owner located? Okay. And if you think of it this way, the answer, we can't give you the exact answer. We can't tell you that the owner is located exactly at 30.7 or 20 8.6, okay? We have no idea where the owner is exactly located, right? But we do expect the owner to be close to the dog, okay? And so what we're gonna try to do is we're gonna try to create like a range of where we believe the owner could be, okay? And we know some things about the behavior of the dog, okay? We don't really know the behavior of the owner, but we do know behavior of the dog, okay? In general, the dog likes to stay close to the owner, okay? The dog doesn't like to go super far away from the owner, doesn't like to pull against the elastic leash. And so 68% of the time, the dog is gonna stay within 1 yard of the owner. 95% of the time, the dog is gonna stay within 2 yards of the owner. And almost 100% of the time, 99.7% of the time, the dog will stay within 3 yards of the owner, okay? So maybe that sounds familiar. And so this is kind of the key statement that we're gonna make, right? Based on the behavior of the dog. So we understand the behavior of the dog. What we can say is that if we see the dog located at 30, then we can be 95% confident that the owner is between 28 and 32, right? And I want to kind of pause here and make sure that this statement makes sense. That because we understand the behavior of the dog, when we see the dog at the 30, we can be confident that the owner is between 28 and 32, right? Because 95% of the time, the dog likes to stay within 2 yards of the owner, okay? Now, does this guarantee that the owner is between 28 and 32? The owner is not guaranteed to be between 28 and 32. The owner could very well be at 33. The owner could very well be at 33.5, could very well be at like 27.5 or 26.5 or something. Could be, the owner could be more than 2 yards away from the dog. Okay, but that would be surprising to us, because then that means that this picture happened to be taken at one of those rare moments where the dog chose to be more than 2 or 3 yards from the owner. Okay, so it happens, the dog can be more than 2 or 3 yards from the owner, but it's a pretty rare thing. And so when you see the dog located at someplace like the 30, we're going to kind of place, hedge our bets, I guess, and say, I'm pretty confident that the owner is going to be within 2 yards of the dog. Okay, because 95% of the time, the dog stays within 2 yards of the owner. Okay, so that's kind of the premise that we're going here, right? And the analogy is that the dog and like based on the dog trying to figure out where the invisible owner is kind of like the idea of you get to see the mean of your sample and you're trying to figure out the mean of the population, right? The location of the mean of the population is unknown to us, right? Much like the location of the invisible owner. We don't know where the owner is. We don't know where the mean of the population is, okay? But on the other hand, we do know where the dog is, and we do know where the mean of our sample is, okay? And the idea is we can see the sample mean and we see Y bar, and based on that, we want to figure out where the population mean mu is. Earlier, the first half of today's lecture was all about the sampling distribution and the central limit theorem. And we said that the sampling distribution follows a normal distribution. And basically the normal distribution says that most of the time, or the normal distribution says most of the time our observations are within 2 standard deviations of the mean. And the central limit theorem basically says most of the time Y bar is going to be within 2 standard errors of the population mean mu. Okay, and so because we know the behavior of Y bar, we can be 95% confident that the population mean mu, which is unknown to us, is going to be within 2 standard errors of Y bar. Right, and that is the central idea of the confidence interval, is that we know that the mean of the sample follows the central limit theorem which says most of the time, the sample mean is going to be close to the population mean. And so when we see the sample mean located somewhere at, say, 30, we can be confident that the population mean is close to it. Okay. But again, all we can do is really just create a range of values where we believe the population mean is. We can't precisely say for sure the population mean is located exactly here. All right, and so to kind of formalize this a little bit, we can say something like this. We can be 95% confident that the population mean mu is between, and we're going to basically go down 2 standard errors and up 2 standard errors, okay? So, technically, a more accurate number is 1.96. So we're going to go 1.96 standard errors down. Each standard error is sigma over the square root of n. So basically, you know, to come up with the numbers 28 and 32, we did 30 minus 2 yards and 30 plus 2 yards. And basically, I'm going to take the value that we observe, y bar, and we're going to go down 2 standard errors, or technically 1.96 standard errors, 1.96 times sigma over the square root of n, and y bar plus 1.96 standard errors. Okay. All right. Is this okay? Kind of the logical progression that I've been stating to get us here. Okay. Thank you for your thumbs up there. I appreciate that. Okay, so there's a catch here, all right? There's a problem. And the problem is we don't know what the sigma is. We don't know the population standard deviation, okay? Because, well, I'm assuming we don't know sigma because the whole idea here is we don't know what the population mean mu is. We get to see our sample means y bar, but we're trying to say, okay, well, based on my sample mean, what is my population mean? Okay. Oh, question. Where did 1.96 come from? Okay. It comes from the normal distribution. We've been kind of saying go approximately 95% are within 2 standard deviations of the mean. But the truth is that a more accurate number is 1.96. And if you look at the normal distribution, if you want the middle 95%, you want 2.5% down here, 95% in the middle, 2.5% up here, right? So you got 2.5%, 2.5%, 95% in the middle. So if you're going to look for where is 2.5%, it's at 1.96, negative 1.9, and column 6, you get 0.025. Okay, so that's where we're getting 1.96. It's just it's a number that's a little bit more accurate than 2. Okay, well, for simplicity, we've just been saying 2 standard errors, but a little bit more accurate to say 1.96. Okay, but we're in a situation where we don't know sigma, right? We know the sample mean, we know the sample standard deviation, but we don't know the population mean. And I'm assuming we don't know the population standard deviation because I can't imagine a situation where you know the population standard deviation, but you don't know the population mean. So we're in so we don't know what the population standard deviation is. Okay, so what are we supposed to do? If we have no idea, or if we don't know what the standard deviation of the population is, how can we go up or down 2 standard errors? Okay, well, we're going to just do the best we can. Okay, we say, well, we have a sample. Okay, we have a sample, and what I can do is I can take the standard deviation of my sample, and we're going to say this standard deviation of my sample will serve as kind of my best available guess or best estimate that I have available to be these, and we're going to use that as the estimate of the standard deviation of the population. So I don't know what the standard deviation of the entire population is. I do have a sample, and I do know the standard deviation of my sample. I can calculate, right? You just plug numbers into your formula, you get a standard deviation of your sample. And we say, okay, well, this has to be a decent guess for what the standard deviation of the population is, okay? And so what we're going to do is we're going to say, let's estimate the standard error. Instead of doing sigma divided by the square root of n, let's just use s over the square root of n, okay? And we say, okay, well, that's fine and all, but it does introduce extra uncertainty, right? Because now we're like guessing another thing, okay? So we've got an extra bit of uncertainty. And so the way we're going to compensate for this extra uncertainty is we're going to kind of fudge our numbers a little bit, right? Because we don't know if the standard deviation of my sample is too big or too small compared to the standard deviation of the population, right? We don't know if it's bigger than sigma or smaller than sigma. And if you have a standard deviation that is smaller than sigma, that could lead into some problems because your resulting confidence interval is going to be a little bit too narrow and you can end up making the wrong conclusion. So we're going to compensate for this uncertainty by intentionally making our confidence interval a little bit wider. Okay, so rather than going up or down 1.96 standard deviations, we might go, or 1.96 standard errors, we might adjust that number and bump it up a bit and say, you know what, let's go up or down 2.1 standard errors, right? So let's just kind of, add a little bit of a 10% margin, 10% safety margin or something like that, right? So instead of going up or down 1.96 standard errors, we'll go up or down, say, 2.1 standard errors or something like that. Okay. And so how we're going to do this is guided mathematically by something called the t-distribution. Okay. And we're not going to get into the derivation of the t-distribution or anything like that. If you decide to study more statistics, you could take a mathematical statistics course where you get into where the t-distribution comes from. T-distribution looks a lot like the normal distribution, except it has what we call thicker tails. Basically, instead of going out 1.96 to get 95%, you have to go out something a little bit more, like 2.1 to get 95% in the middle, okay? But it's not just 2.1 universally. How much you have to compensate depends on your sample size, okay? And I think this makes sense, right? If you have a really big sample, if your sample has like 1,000 people in it, then when you take the standard deviation of your sample, you can expect the standard deviation of your sample to be a very good guess for the standard deviation of your population. Because you got like 1,000 people in your sample, the standard deviation of your sample should be a pretty good guess for the standard deviation of the population. Okay. On the other hand, if you have a really small sample, let's say you have a sample of say 5 people, right? And you calculate the standard deviation of your 5 people. Okay. Standard deviation of your 5 people, that could be wildly off from the standard deviation of the population, right? It could be quite a bit different. So if you have a big sample, the amount you need to compensate is just a tiny bit, right? But if you have a small sample, you need to compensate a lot more, okay? And this is factored into the t-distribution. So the t-distribution uses something called the degrees of freedom. Okay, so I think this is what I've written in this paragraph. If our sample size is large, we can expect our sample standard deviation to be a good estimate of sigma. Our value only needs to be a tiny bit bigger, so we might use 1.99 instead of 1.96. On the other hand, if our sample size is small, our standard deviation could be a bad estimate of sigma. We factor this in and we use a value that's a lot bigger. So for example, we might use 2.365 instead of 1.96. Okay, and so this is factored in the t-distribution with something called the degrees of freedom. Okay, and so as far as our confidence interval in this chapter goes, our degrees of freedom is found by using n minus 1. N minus 1, okay? And so as the degrees of freedom approaches infinity, the t-distribution values will end up matching the normal distribution values, and you're going to use 1.96, okay? This concept of degrees of freedom is weird. And I'll just kind of illustrate it with one example. It's a very, very, very loose example. And it's just kind of the idea of, how much freedom do you have if like there's a statistic kind of set in stone. So for example, we could say, let's play a game. As a class, I will let you guys pick, we're going to pick 10 numbers together as a class. And I will guarantee that the average of those 10 numbers is going to be 100. Okay. The average of those, I can guarantee that the average of those 10 numbers will be 100. Okay, we're going to pick 10 numbers. Okay, there's one thing, and that is I get to pick the last number. Okay, and if we do that, then you can see, okay, that's easy, right? You guys, as a class, you guys can pick the first 9 numbers. Okay, you're free to pick whatever you want for your first 9 numbers. And as long as I get to pick the very last number, that 10th number, I can make sure that all of the numbers, whatever it is, they add up to a 1,000, and then the average of those 10 numbers will be 100, right? So you could pick really highly big numbers or really small numbers or negative numbers, and I just have to figure out, okay, how do I make sure all 10 numbers add up to 1,000, and then the average will be 100. So you know, you are free to pick 9 of those numbers, and then the last one is kind of locked in to kind of get it. And then that's kind of a little bit of the idea of the degrees of freedom. We have n-1, and you could play like more complicated versions of the game where we can say, all right, pick some numbers, and the mean is going to be this number, and the standard deviation is going to be this other number, and then you would have n-2 degrees of freedom, and you know, the game gets more and more complicated, but as you put in kind of more conditions, you lose some degrees of freedom here. But anyway, as far as this thing goes, we're going to have n-1 degrees of freedom, and it kind of reflects how big our sample is. There is an interesting history of the t-distribution, and you know, my lecture is already full of random side stories and things like that. But the t-distribution was actually developed by this man, William Gossett, who worked for Guinness Brewery, right? The beer factory in Ireland. And, you know, you can take a tour and see stuff like that. But he developed the t-distribution. Guinness Brewery didn't, they had kind of like this legal team that didn't want academic articles traced back to them, so they forced him to publish under a pseudonym, and so he just called himself a student, and so for a long time it was known as Students t-distribution, or it still kind of is the Students t-distribution. But yeah, William Gossett. So anyway, I put in some videos on YouTube that you can click and watch if you're interested in the history of statistics. The history of statistics is interesting, but also full of some messed up stuff, because you know, a lot of advancements in statistics were, anyway, you know, people were interested in eugenics and things at that time, and that's why they were studying measurements and statistics and things. So we thank them for their contributions to the field, but certainly not things we are, I guess, proud of. So this is what the t-distribution looks like. And you'll see one column on the left. This is really hard to read, but it's included in your packet of reference tables. Table 4 is the t-distribution, okay? On the left-hand side, you have the degrees of freedom, and across the bottom, you have what's the confidence level, okay? The top says upper tail probability. We will get that, get into that next week. Okay, so we can see for 95% confidence, if we have infinity degrees of freedom, we have the same value from the normal distribution table, and we get 1.96. Okay, and you can see when you have lots of degrees of freedom, say 1,000 degrees of freedom, the amount you need to adjust is very little. You go from 1.96 to say 1.962, right? So the amount you kind of need to compensate for having estimating the standard deviation of the population, the amount you need to kind of compensate is just a tiny bit. But then as the sample size decreases and you have fewer and fewer degrees of freedom, the amount you need to adjust goes from 1.96 to something, you know, 2.262, 2.571. And, you know, if you only have 1 degree of freedom, which would be a terrible, like, you don't want to have only 1 degree of freedom, because that means you have a sample size of 2. This is not a good basis for any kind of stuff. You would have to use a ridiculous value of 12.706. Okay, so that would be that's almost quite useless at that point. But But there you have that, okay? All right, so that's, this is how we would use the t-table. And so let's just try out an example, right? So when we put all of this together, the confidence interval for mu based on a single sample is going to be y bar plus or minus t star being the value that comes from our t-table, the critical value from our t-table, t-table, times the standard error that we've estimated, which is s divided by the square root of n. This entire part over here, the part that we go plus or minus, is known as the margin of error. So sometimes you'll see, you know, polling on the news, and it will say something like so-and-so is, you know, has this, you know, votes favorable with a margin of error of 3% or something like that, right? So that entire plus or minus part is the margin of error. Okay, so let's try an example here. Let's assume that the wing area for a monarch butterfly is normally distributed. Okay, and basically the reason why it says normally distributed is so we can say, all right, let's go ahead and use the central limit theorem for a small sample, okay? And we're going to say we have a sample of 14 random butterflies. So we're going to have a sample size of 14. And we measure their wing areas, the mean area from our sample, right? The mean area of the sample. So it's important we write y bar, not mu, but y bar is 32.81. And the standard deviation of our sample is 2.48, okay? And so the confidence interval, that formula is y bar plus or minus t star times s over the square root of n, okay? So in here, it's just really a matter of plugging in numbers. We're gonna make a 95% confidence interval. So how many degrees of freedom do we have? We have n minus 1, I have 13 degrees of freedom. I have a sample of 14, 13 degrees of freedom. I'm gonna go to the table. We're looking at 13 degrees of freedom. We go to the column for 95% confidence interval. 95% confidence, 13 degrees of freedom. The number I'm going to use is 2.160. And that's just from my t-table. Okay, so the t star from the table is 2.160. Okay, and here it's just a matter of plugging in the numbers now. So I'm going to do y bar 32.81 plus or minus t star 2.160 times s, which is 2.48, divided by the square root of n, square root of 14. 32.81 plus or minus, I'm going to go ahead and I'm going to plug this part into the calculator. 2.160 times 2.48 divided by the square root of 14. Okay, and so this gives me plus or minus 1.43. 32.81 plus 1.43, 32.81 plus 1.43. It's 34.24. So on the high end, I have 34.24, or my upper bound, 34.24. And I do 32.81 minus 1.43, and my lower bound is 31.38. Okay, so that's how I get my upper and lower bound of the confidence interval. Okay, we feel okay about that? So I think I plugged all of this in. I guess I kept more decimal places in the notes. 31.378, 34.242 square centimeters. And our conclusion, the statement we would make, we write this: we are 95% confident that the mean wing area of all monarch butterflies is between 31.378 and 34.242 square centimeters. Okay, I think plugging in all of the numbers is pretty straightforward and easy. Just when you take a quiz, right, you're going to have a quiz this weekend and I'm going to ask you to make a confidence interval. I think this is the easiest part. You just make sure you don't make a silly mistake like with your calculator and you put in the wrong number, right? But, you know, it's just a matter of like correctly labeling, okay, what's my mean, y bar, you know, looking up the value T star in the table. I mean, there's a few little steps that you have to do. None of the steps themselves are hard, but there is potential to make a silly mistake and then you get the wrong answer. So just be careful, take your time, make sure you're plugging in the right values. Okay. A little bit more importantly, though, more important is the interpretations, and you will see a bunch of these interpretation questions on the quiz. Okay. Question: is it fine for us to use only 2 numbers or after the decimal, or should we do 3? I will specify on the quiz how many places after the decimal I want you guys to keep. I don't remember off the top of my head what I put in the quiz, but it will say, you know, keep this many places or this many numbers after the decimal point. Okay, the interpretations are more important, and there's going to be several of these interpretation questions on the quiz. And so we want to make sure we can answer these correctly, right? So our first question, and perhaps it will be a little bit easier if I draw like a number line here, okay? So I'm going to draw a number line. I mean, maybe it's silly for me to do this, okay? And so 30, 31, 32, 33, 34, 35, 36, and we are going from 31.378, which is somewhere around here, to 34.242. Okay, so this is what my confidence interval looks like. Okay, so I'm going to go from here to here. So my confidence interval goes from around here to here. Okay, 31.378 to 34.242. Okay, yeah, inclusive or exclusive, it makes very little difference here. Okay, I guess we can say inclusive. Okay, all right, so the question: do we have evidence that the mean wing area mu is different from 31.0? Okay, 31.0. So the question is, could the value, right, is 31.0 plausible? Okay, so basically values inside the interval are plausible. Are plausible values plausible for mu, right? The population mean. So we're saying the population mean, we're confident that the mean wing area of all monarch butterflies is somewhere in this red zone, right? So we're saying I'm pretty confident that the mean mu is somewhere inside this red zone. This red zone represents plausible values. And so the question is do we have evidence that the wing area mu is different from 31.0? Okay, and the answer here is yes, 31.0 is not inside our interval, right? So 31 is not plausible. And we would say we have evidence that it's not 31, okay? Because 31 is outside of our interval. Is that okay? We have evidence that mu is not 31 because mu is outside of the interval. Okay, now it doesn't necessarily guarantee that mu is not 31. We just say that, you know, the evidence points to it not being 31. Okay, it's just like when you see the dog at the 30, you say the evidence of this picture says the owner is not going to be at 26. Okay, but can we guarantee that the owner is definitely not 26? We can't guarantee that. We can't guarantee that. Okay, so we can't guarantee it, but we can say, yeah, the evidence points to it not being 31. Okay. Do we have evidence that mu is different from, say, 34.1? Okay, what about 34.1? 34.1 is right here. It's still inside our interval. Here's 34.1 It's inside the interval. 34.1 is within the interval. So as far as our interval is concerned, it's a plausible value. It's a plausible value, okay? So 34.1 is a plausible value. So we can't say that we have evidence against 34.1, okay? We cannot say that we have evidence that mu is something different from 34.1. So as far as 34.1 goes, it could be it, okay? Could be it. We're not saying that it's for sure 34.1, but we're saying it could be 34.1. Okay. Can we say that we have evidence that the mu is equal to 32.2? Right, so here is, so we look at our interval, 32.2 is inside the interval. Could it be 32.2? Or is it? Is mu equal to 32.2? Is mu equal to 32.2? Right, and the answer is no, okay? We can't say that mu is definitely equal to 32.2, right? That would be akin to saying, based on this picture, I see the dog at the 30, then I'm guaranteeing that the owner's at 30.2. Okay, we cannot say that the owner is definitely located at some location. Okay, the confidence interval just says this is the range of plausible values, but it doesn't say that the value mu is equal to any one of these exact values. I hope that's okay. All right, let me go ahead and give you your last view quiz answer for today. The last view quiz answer for today is E. E as in elephant. E as in elephant. Okay, I still have a few more slides to cover, so don't go anywhere yet. Okay, E as in elephant is your last view quiz answer. Right. What happens if we change the confidence level? Okay, if we change the confidence level, it says we want to be more confident that the interval contains mu, right? If we want to be more confident that the resulting interval contains the value mu, what we have to do is we've got to make our interval wider, right? And we want to make sure that mu is in there. We say, all right, well, I got to make our interval wider, okay? So you can say, well, why don't I just make a 99.99% confidence interval or 100% confidence interval, okay? Higher levels of confidence result in wider intervals, but wider intervals are not very useful, okay? Narrower intervals are more useful, okay? But it comes at the cost of giving up confidence, right? So for example, let's say you're doing some planning for next year. You're gonna make a budget for yourself, or maybe not for yourself. Let's say in the future, you're running a business and you say, well, okay, what's our income gonna be for next year? And you can say, well, I'm 100% confident. Somebody could, try to be smart with you and they say, well, I'm 100% confident we're going to make somewhere between $0 and $10 million. And you go, haha, that's not funny, because, if you give us a range between $0 and $10 million, sure, we're going to be guaranteed to be right there, but it's not useful, right? You can't do any kind of budget planning if the range goes from $0 to $10 million. So you say, okay, well, you're running a small business here and you say, okay, well, maybe my revenue will be between, I don't know, 190,000 and 220,000, right? So that's a much more narrow range, and perhaps that's something more reasonable that you can work with. 190 to 220,000. Now you can start doing some monthly plans and things like that. You have a budget that you can work with, okay? But it comes at being less confident, right? You might end up being wrong and you might make less than that, or you might end up being wrong and make more than that, right? Because when you have a much more narrow interval, and the true value can end up being outside of that, right? So narrower intervals are more useful, but you'll be less confident. Okay, so when we make a 95% confidence interval, this is using that data that we have, this is the resulting interval. And if I do the same thing, but I say, you know what, I want to make a 99% confidence interval, okay? When you switch from a 95 to 99% confidence interval, the only thing that's going to change, right? You have the same Y bar, you have the same standard deviation, you have the same sample size. Okay, none of your values from your data change. The only thing that changes when you go from a 95 to a 99% confidence interval is the critical value T star. When you have 95% confidence interval, 13 degrees of freedom, you have 2.16. If you have a 99% confidence interval, critical value for confidence 99%, 13 degrees of freedom, we use 3.012. Okay, so changing our level of confidence changes the critical value T star. Okay, and so at 95% confidence, our interval goes from 31.378 to 34.242. The 99% confidence interval becomes wider and goes from 30.814 to 34.806. Does that make sense? Okay, so increased confidence, you got to make a wider interval, right? If you want to be more sure that you're going to catch the invisible value of mu, you just cast a bigger net. You cast something a little bit wider. Okay, so this leads to a slightly unusual situation. I don't know if that's unusual, but let's ask this same question. Do we have evidence that the mean wing area is different from 31? Okay, so I already deleted it. Okay, well, if we look at this interval, 31.378 to 34.242, 95% confident, 31 is outside of our confidence interval, right? 31 is outside of our confidence interval. We say, yeah, 31 is not plausible. I have evidence that the mean wing area is different from 31. Okay, so we say 31 is not between there. It's not a plausible value. I have evidence that the mean is different from 31. Okay, let's look at the 99% confidence interval. Same data, 99% confidence interval. Okay, that confidence interval goes from 30.81 to 34.8. Do we have evidence that the mean wing area is different from 31? Okay, now 31 is inside the interval. 31 is between the ends of the confidence interval. It's considered a plausible value. And so this one, we say we cannot say that we have evidence that mu is a value different from 31. All right, so one, we say, at 95% confidence, we say, yeah, I have evidence that it's not 31. At 99% confidence, I'm saying, no, I don't have evidence that it's different from 31. Okay, so we're making like two opposite conclusions here. Same data. The only thing we changed was the level of confidence. And so the question is, are these conclusions in conflict? Are these in conflict? And the answer is they are not in conflict. The difference that we're seeing here reflects the difference in confidence levels, okay? It reflects kind of the change in confidence. It's kind of, you have different tolerances for risk, right? You have two people, they can look at the same situation and one person has a greater tolerance for risk and the other person has a lower tolerance for risk, and they could end up making different conclusions. The same data is available to them, right? This person says, you know what? I'm okay with being only 95% confident in my answer. At 95% confident, I'm ready to reject this number. 31, let's not even worry about it. It's not going to happen. We don't have to plan for the situation where the answer turned out to be 31, okay? Someone says, no. If we're wrong, it's a big problem. So we got to be really sure before we start eliminating stuff, right? So if you want to be 99% confident in your conclusion, you have to be a little bit more cautious and you won't be ready to eliminate 31. You say, well, you know what? There's a small, like it could be 31. I want to be prepared for that situation. So we're going to kind of plan for that scenario, if that kind of makes sense, right? So two people, depending on their levels of tolerance for risk, could end up making different decisions, even though they're presented with the exact same data. And it's not that you can do, like, this is one thing that always offends me a little bit is people say, well, you can lie and say whatever you want with statistics, okay? You can conclude whatever you want with statistics. That's not the case, right? We're like pursuers of the truth, but it is true. People can make different conclusions based on their level of confidence that they want to work with, okay? Okay, oh, I know I'm over time here. there's one thing. So far, we've been using this phrase, I'm 95% confident, okay, that the area is between here and here, okay? Now, what we want to avoid is we don't want to say this. There's a 95% probability that the wing area is between this and this, okay? We want to say, we can say I'm 95% confident. We don't want to say there's a 95% probability, okay? And so the difference here is if I flip a coin, before I flip a coin, I can say, what's the probability that the coin will land heads? You say the probability is 0.5. Okay. All right. I flip the coin and I ask, what's the probability that the coin has landed heads? And you go, 0.5. All right. Now watch what I do. I look at my coin, I cover it back up, and I say, what is the probability that the coin has landed heads? All right. And so now you're confused and you still go 0.5, maybe 1, maybe 0. I'm a little bit weirded out, okay? Well, the answer is that after the coin landed, the question, what is the probability the coin landed heads, is a nonsense question. The coin either landed heads or it didn't land heads. There's no probability anymore. Probability only exists for events of things that are uncertain. Before I flip the coin, I can talk about probability, whether the coin will land heads or not. Once the coin has landed, there's no probability. It either landed heads or didn't land heads. So we can't talk about what is the probability that the coin landed heads. It's a nonsense question. There's no probability, right? It just doesn't make sense, right? So when we talk about the mean of the population, it's some value, right? If we could freeze time and capture all the butterflies and measure their wing area, there is a mean value and it's some fixed number. We just have no idea what it is, but it doesn't make sense to talk about the probability of that number. That number is not subject to probability or randomness. So that number is either going to be in your interval or it's not, but it doesn't make sense to talk about probability. We don't know whether it is in that interval or not, so we can talk about confidence, right? When you don't know how the coin flip landed, you can't say there's a 50% probability it landed heads because it either did or didn't. But you can say I'm 50% confident that it landed heads, okay? So you can talk about confidence, but you can't talk about probability. Okay, we will end there. This is just another example that I've worked through where I give you some raw numbers and you can kind of read through it in the on your own time for how do you create a confidence interval if you just give some raw numbers here. Okay, but I apologize. Thanks for being patient. Apologize for going over time today, but we will end here. And so I hope you guys have a good weekend. As always, you will have homeworks due on Sunday. You have a quiz also due Sunday evening. So be on the lookout for that. Okay. All right. Thank you and have a good night. If you have any questions, I'll stick around for office hours. If not, have a good weekend and we'll see you guys on Monday.